of this community because the name tells me a lot. The name tells me that you all are experts in quantum world and quantum physics, quantum computing, or I do not know which kind of quantum this is, but it's certainly a privilege to be with all of you this evening. I would like to share with you whatever little I know, whatever little I have learned, and whatever exciting adventures I have had as a particle physicist at CERN in Geneva. And please feel free to ask me questions, because it's really not about giving a presentation or just showing you what CERN is and what is the great work going on. It's really about a dialogue about could people who are not talking, please, could they mute?
Balaji, can you mute everyone but the speaker?
Just a minute. Okay, Archana, please go ahead.
Yes. So essentially, all of us have had questions ever since we were children, and we continue to have those questions. Why at all are we here? And it is in the search of these answers is where philosophy, science, religion, spirituality, and in some sense, the search for answers to these questions is what brings us together as well. The questions are, where did we come from? What is the world made of? And what holds it together? It is indeed such a wonder that we live in a world where everything around us goes around with precise laws and forces which we still have to understand fully, still have to comprehend, and still have to digest the magnitude of all what goes on around us. So it is in search of these kind of answers that we are trying to look at the universe around us, and if at all there are multiverses out there. So many of you may have seen this picture before. Here, what is shown is the pictorially the Big Bang that happened about 15 billion years ago, 14.7 billion to be precise. At that moment of time, there was a singularity that happened, because of which something gave rise to a cosmic soup, a primordial cosmic soup, where the temperatures were million times higher than that inside that of the sun. Slowly, very slowly, in fact, initially very rapidly, this whole soup started cooling down. And as time progressed, in about 3 minutes, what we see as particles, what we see as elements, they came about. And from there on, as you know, that there were molecules, and the molecules then created other compounds, and slowly over the billions of years, we see the world all around us. So in some sense, all of us are made up of this stardust, of this cosmic soup. So eventually, at the point where we are today, where we are thinking about these questions, we really have come a very long way, and we would like to understand how this has happened, or at least the state of matter that existed at the time of the Big Bang, or at least a few seconds, a few minutes after the Big Bang. And that's what are the adventures that go on around us. I live in Geneva, Switzerland, and here you may have heard about a laboratory called CERN, C-E-R-N. It's an acronym, a French acronym, Centre or Conseil sometimes, Européen pour la Recherche Nucléaire. So that laboratory is close to the airport. As you see here on this slide, you see an airport, and on the left of the airport, my left, is really the way that we go down to CERN. And what you see buzzing around is a schematic of an accelerator. And I'll come to that in a moment. So let's look at the scales of magnitudes, which you all are very familiar with as far as I can tell. The scales are really from the mega scales, talking about the radius of the Earth, the distance from the Earth to the Sun. If we go further, the radius of the galaxies and the universe itself, where we are looking at those scales using objects like the Hubble telescope, or we are looking at experiments in the International Space Station like the alpha magnetic spectrometer, the AMS, which also is housed at CERN for the preparatory phase. Then there are, of course, measurements done in cosmology. So that's the range of the larger dimensions that we spoke about. Coming to the smaller dimensions, how do we look inside matter when we go towards the smaller dimensions? And ever since time, people have been breaking down matter and looking, first of all, examining it, and then looking inside a microscope to understand what's inside matter. And smashing matter together, like particles, like protons, we are able to use a very highly precise microscope, so to speak, called the Large Hadron Collider. That's what is housed in this schematic circle of 27 kilometers, 100 meters underground, below the Alps, below the Jura Mountains, in the Geneva region. So yes, that's where we want to investigate by using a property which all of you know, and the only equation that I'm going to use is E is equal to mc squared. So when these two protons will smash together with very, very high energies, we are able to study the first 10 to the minus 10, 10 to the minus 5 seconds of after the Big Bang. And the experiments that we work on look at the phases, so to speak, as the electroweak phase transition or the quark-gluon plasma, which is the QCD phase transition. Don't worry about these words. They are simply denoting the period of time that existed after the Big Bang and what are the kind of phase transitions of matter, because it was not gas or liquid or solid as we know today at that moment of time. So what was this matter? And that's what we are trying to understand. So yes, we can create by using E is equal to mc squared. Two beams of protons, they collide and they generate in a very, very tiny space temperatures over 1 billion times higher than those prevailing at the center of the sun. And what is the real fun here is that we can produce particles that may have existed at the beginning of the universe right after the Big Bang. So you know particles around you, protons, electrons, neutrons, but then there are other particles that may have existed at the time of the Big Bang and they do not exist anymore. So those are the dinosaurs we are interested in. Now let's look at the 4 experiments. And these are the 4 experiments, the underground experiments that I just mentioned to you. On the surface, this is a schematic again. There is Switzerland on one side, there is France on the other side, and down below, across the 2 countries, is the Large Hadron Collider. And of course, the protons, they go through these pipes in vacuum down below over here. The accelerator system is here without having to worry about the border, obviously. And the cows that are grazing on top, also, they do not have any idea of what's going on underground. Now, let's see, why can't I change? Yeah, so these are my protons and they are buzzing through, thousands and thousands of them inside the Large Hadron Collider. So according to the knowledge that we have up to now, we do know that the atom is of the order of 10 to the minus 8 centimeters, the nucleus is of the order of 10 to the minus 12 centimeters, the proton is minus 13 centimeters, and the quark is approximately 10 to the minus 15, 10 to the minus 16 centimeters, and so is the electron. We know that quarks and electrons are the smallest building blocks of matter. Now the question will arise, are there still smaller particles? Are these the fundamentally smallest building blocks of matter? So the Large Hadron Collider is addressing this question. And of course, the other point I was making was about the forces of nature, because how do we understand the planets and the stars that are around us? That's because of gravity. You all know about electromagnetism that gives us light, radio waves, and also it holds atoms together because of the electromagnetic force that the electron and the proton have. Then there's the strong nuclear force which holds the nuclei together despite the positive charge of the protons. And there's the weak nuclear force that gives us radioactivity. Together, these four forces make the sun shine and makes our days and nights, of course. So we have now understood the structure of matter. We have understood also the families of quarks that exist. They are the three families, as you see here in this table. And they are the quarks and leptons, the light particles and the heavy particles. They are the fermions and the bosons that actually enable the forces to happen. So the strong nuclear force enables the strong particles to operate. And of course, I will not go into detail here, but just saying that each of these bosons are there for the force to actually happen. The nuclear force will actually happen because of the gauge bosons W and Z bosons. Similarly, the strong nuclear force is because of the gluons and the other properties that we have of the quarks. And the photon is much more known to us, and we understand better the electromagnetic force. But what exactly is hiding underneath over here is another boson, which probably we do not understand yet, explains the origin of mass. Because in principle, all these quarks and all these other particles should be massless because they are point-like, but they all have mass and very different kinds of masses. And there's the structure, the hierarchy is also not really respected. So we do not understand why this happens. So this led to a large, long program of the physics program at the Large Hadron Collider. It is a very, how can I say, project that has been spanning already 3 decades. It started being discussed in the 90s and produced in the late 90s, early to the noughties. And then after the construction, the first data taking started in 2010. So imagine I had been already watching this project for 15 years when we started taking data for the first time. Today, we have more than 1,000 reviewed scientific papers per experiment. So we definitely are sitting on an adventure which is extremely exciting, extremely long, extremely challenging, but then we are here to answer very fundamental questions. Are the quarks elementary particles? We said so far, yes. After all the data that has gone in there and thousands of physicists who have been looking at this data, the answer still says yes. Do we see supersymmetric particles? Supersymmetric just means another set of particles that explain the fact that we see only 5% of the visible universe. Where is the remainder? Is that real matter? Is there an asymmetry? We still have seen no signs. Do we see any extra dimensions? Not yet. Do we see micro black holes? No, we do not see. So what do we see? We have seen a fantastic discovery of a Higgs-like particle. And Higgs, if you remember, is this corner here that's hiding a boson that's called the Higgs boson, which actually attributes mass and gives mass to all the particles. And it was the only missing component of the standard model, and this is the table I'm showing you is called the standard model of particle physics. So in 1964, some physicists got together and they started asking themselves these questions. Why do some particles have mass and others do not have? And this was 1964, long time ago. And they proposed an explanation of how particles could get mass. It was very interesting to understand that this was a theoretical, mathematical postulate, how a kind of particle that, given a field around it, can give mass to other particles. And this was the esteemed scientists Kibble, Guralnik, Hagen, Engler, Brout, and Professor Peter Higgs, who came up with this theory that the more a particle interacts with this invisible field, the more mass it gets. So this was very interesting. But how can we prove that it exists if the field is invisible? Imagine in 1964, in a mathematical construct, all these people have created a field, an invisible field, because of a particle, and the more any particle interact with this field, it gets mass. However, how to prove it? It was very difficult, obviously. And so that's what was called the Higgs boson, and it completed the standard model. And how do we go hunting for the Higgs? It's really a problem like finding a needle in the haystack. We need very, very high energy because the Higgs is very heavy. It's extremely heavy to produce and very rare as well. So if the probability is 1 in 10 to the 14, imagine the amount of data that we will need to actually create a Higgs boson. So without going into too much detail, to just tell you that it was found in an equivalent time of 48 years in 2 years of data taking at the LHC. So there we are. I'm just illustrating the experiment here. So when you have two protons, consider these two mosquitoes as two protons, and they collide. When they collide, the energy available, E is equal to mc squared, and m is a sum of all the particles that you see coming out. And in this illustration, since we started with mosquitoes, we see animals coming out. Some of them are known animals, which means known particles, like the proton, neutron, electron, neutrino, and so on. But then there could be particles which we have never seen, and they could be unsuspected, extinct particles since the Big Bang. And those are the particles we were very interested to see. And in between, you see here a very heavy Higgs as well, which then immediately decays. And that's why it becomes extremely difficult to catch the Higgs, because it will not stay there for you to look at with a microscope. It will disappear. But fortunately, our experiments and theories tell us how to look for the Higgs boson. It requires many, many people, of course. It's a very big collaboration that is needed, simply because the tools that were needed before we were designing the experiments did not exist. So we needed accelerators, the Large Hadron Collider I described to you. We need detectors. These are gigantic instruments that can record the resulting particles as they are coming out of the collisions. We need computing to collect, to store, to distribute all the huge amount of data, the humongous amount of data that's coming out of these detectors. And clearly we need thousands of students, scientists, engineers, technicians, and of course support staff to design, build, and operate these complex machines. When I started my career, I was not able to fathom the complexity of these kind of experiments. And today, when I look back, it is an incredible learning personally for me, and for anybody who is exposed to this kind of science, these kind of mega projects, and the kind of collaboration that is needed to actually come to goals that are anywhere close to what we are doing here. So the Large Hadron Collider itself, just to show you a picture, it's 27 kilometers in circumference. It's made out of 1,232 pieces, like the one you can see over here. And what exactly is happening inside here? Exactly what we said before. These are the two beam pipes. And inside each beam pipe, there is a beam of protons running in opposite directions, and they are made to collide at the points where there are the experiments. And of course, it is a discovery machine. It will run until 2035 at least, from what I know, and that the luminosity and the intensity and the energy will all be upgraded as well for the future runs. So this is indeed an extraordinary machine, and it runs 1.9 K above absolute zero. So it's a very cold cryogenics. Imagine 54 kilometers of cryogenics that is needed to actually operate this machine. Vacuum system is imagine very, very important, not only to cool the whole thing, but also to have the protons go through the beam pipes. So the vacuum, keeping the vacuum is very important as well. And I already mentioned about the temperature that for very small times happens inside the experiments. So these are the experiments, and they look like 6-storied buildings. They are very, very large, complex machines. And if I just take your attention on the right-hand side, that's the experiment where I work. That's called the Compact Muon Solenoid. So compact, it looks like, simply because it is in comparison with the other experiment a bit smaller, but it's much heavier than the Atlas experiment. So this is 14,000 tons, if I'm not mistaken, and the Atlas experiment is about 5,000 or 6,000 tons. It looks like a cylindrical onion, and each cell of this onion is like a very high performing camera, which is taking pictures 40 million times a second to produce the data for the physics that we just spoke about. These are just some pictures to show you our working places. You can see my colleagues here trying to fix something on part of the detector. More pictures from the experiment, directly from the experiment. This one piece itself, the weight of this piece is 2,000 tons, and manipulating them, the mechanics, the engineering that goes on behind is also mind-boggling. How will you be lifting such a piece which is built on the surface and then lowered down in the cavern? It's an interesting exercise for engineers to think of. And here we are with some of my detectors that were recently installed. And you can see this is the tool with which one of these detectors is being installed. Now, once you have your machine and your experiment, then of course there is a challenge of the data, because the amount of data we are looking at is unbelievable. When we started the experiments, we thought that we will have data of the order of 15 million gigabytes. But what actually came out in 3 years was 5 times higher. So even evaluating what are the needs for data and data analysis is very difficult. So we are getting better at the game as we are going further and further. And CERN alone does not have the capacity to manage all the data. And that's why we go for grid computing, which is a tier system all over the world, where tier 0 is CERN, and immediately the data is shipped out to tier 1 centers, where the data is stored, processed, and analyzed, and then also made available to the tier 2 sites, where again, the data is analyzed and shared with all the collaboration all over the world. Mind you, I did not mention that the collaboration is made out of, I think, 250 institutions coming from 50 countries. So it's a huge, huge collaboration with over 5,000 collaborators. So now we are hitting another end with data, which is now, the previous part I mentioned was when we started the experiment into 2010, and now the CPU scaling is really coming to an end because of the limits of transistors. So we are going to move to GPUs probably in the next phase, and the kind of events that we are going to see is going to be massive. So we need now to prepare for exabytes. So these are again challenges for our computer engineers to foresee what are the kind of computing needs that we will have, what are the kind of machines that will be needed for the next phase of the experiment. So in line with what's going on in the world, of course, high energy physics is one place where we start off new trends of how artificial intelligence will work, and the way we develop algorithms and the way we have used machine learning in our collaboration to track data, to track events, is then picked up by the rest of the world, and it's used in many, many other fields, which I will tell you later on. So these are the kind of collisions that we will look at. The protons come in, and then how the Higgs will decay and how we will recognize it. And by now, the LHC is a factory for the Higgs, and millions of Higgses are produced, something like 15 Higgs per minute every time we have been running the LHC. So these are plots which are not here for going deep into, but just to show you the excitement that has been going on in the two experiments, ATLAS and CMS, during summer 2012. And it was just a little blip that you see here that got everybody very, very excited. And this was ATLAS. And CMS also saw a similar blip, but in another channel of decay of the Higgs. So in 3 different ways, we saw the Higgs decaying in 2 different experiments. And of course, given all the statistics and given all the studies, given all the verifications, given all the confidence building measures, eventually it was declared that this was a Higgs-like boson. And the official announcement came on the 4th of July 2012, when we discussed and we announced to the world that there was a Higgs-like particle with a mass of 125 to 126 GeV by CMS and ATLAS. And there was a historic seminar at CERN with a simultaneous transmission and live link at the large conference going on at that moment in Australia. I was there at 5 o'clock in the morning to get admission into this room, and I did not get admission in the room. So I had to unfortunately watch it live from another room. Of course, it was quite big news. Everybody heard about it. And 1 year later, the Nobel Prize was announced for Francois Englert and Professor Peter Higgs for discovery of the Higgs boson. And subsequently in December, in the ceremony, the Nobel Prize was given for the proposed theory of the mechanism that contributes to our understanding of the origin of the mass of subatomic particles. And of course, it was confirmed through the discovery by the experiments ATLAS and CMS at the CERN's Large Hadron Collider. So what a humongous effort. What an effort over decades to start from a theory and then to look for those particles in an experiment. So what is now in the future? We have worked for 25 years to look for the Higgs boson. We found it, and now what's next? There are many questions that are still unanswered, and for that we are upgrading the machine, we are upgrading the experiments, and of course we are looking for answers which are still out there, open questions. I will not go into detail, but probably, yeah, or maybe perhaps I will mention about the antimatter. You must have a question in your mind that why at all are we here? Because if at the time of the Big Bang, the matter was created, an equal amount of antimatter should have been created, and thereby we should have annihilated immediately, and there should not have been any matter left, isn't it? Just because of conservation. But we are here. Matter is all around us. So there must be some difference between matter and antimatter. Something happened where only matter remained. So these are very interesting questions to look at. So we are searching for those kind of new physics, and similarly for dark matter and dark energy as well. We are looking for signals if we can find some candidates of dark matter and signals for dark energy in our experiments. which has already been proposed by Zwicky and Vera Rubin in 1970, in the 70s. Okay, so all that's excellent. We are doing a lot of work and a lot of exciting experiments. But then as a common man, as a person in the society, why at all should people bother? Why should we invest so much in particle physics? And why at all should we fund experiments which cost so much and last over decades? I think personally, of course, I'm very committed to what I do, and so is every person who works in the field. And we are very proud of the fact that every innovation that we do not even know when we are starting to build an experiment ends up with an impact in the society. So here, what we are trying to do is to interface fundamental science and the key technological impacts. And all that comes from accelerators, where we are accelerating particle beams, we are detecting particles, and we have the large scale computing grid. So these are the tools that we use at CERN, and these are the tools that we can turn around and use for the society as well. So the accelerators, many of you might know already that more than half of the accelerator in the world, and this number is a bit old, I have to upgrade it. They are used for medicine, for hadron therapy, for treating cancers, and detectors are used for medical imaging and for positron emission tomography, which uses antimatter. Medical application, there are many applications. I mean, I'm not going to go through those details, but it's just to tell you that here we are. I did update it, so I have to just, the previous slide needs some correction. Accelerating particle beams, we have 17,000. So just imagine the number that has gone over the last 10 years and how many patients have been treated worldwide, simply because if you use protons for tumor therapy, then all the energy of the projectile, the proton, is deposited at a single point. You see in this particular picture on the right, all the energy from a proton can be deposited at the point of the tumor. While if you go with an X-ray, you are actually illuminating most of the remainder tissues, and unfortunately, those are the risks for patients. And with protons and other ions as well, you are able to treat the patients in a much improved manner. And similarly for the PET scanner, we have lots and lots of examples. Then when you use simulations, the computing powers, there are so many of these packages you may have heard. Let me give you just one example, that if you have to treat a patient and give him a dose of protons, you have to first do a simulation to make sure what should be the energy of the projectile that you're going to use, and what is the tissue where the tumor is, how much it should go inside, because you can fine tune just like a digital scalpel where you want to deposit the energy from the proton. So to do that, you need to do simulations, and those simulations are very well mastered in our field, and those are called FLUCA. This is just one example I'm going to give you for the moment here. Of course, the World Wide Web, how can any talk be complete without speaking about the World Wide Web that was invented by Tim Berners-Lee when he was a student at CERN. X-rays we have already spoken about, and digital imaging also we have spoken about. I particularly like this slide simply because when I studied and when I was working on mathematics in my school years and in my college, it was very hard for me to visualize all the kind of differential equations, the polynomials, and all the rather difficult mathematics that I had learned. But when I saw this in action once, just by a simulation, which of course uses a lot of computing power and thereby not readily available in schools, for today, every school on the planet actually has access to all these kinds of things where an equation, a mathematical construct can be visualized. Similarly, for bioinformatics, for gene therapies, simulations, the LHC grid can be used. The weather forecasting is very intensive in terms of computation power, and there, of course, distributed computing allows remotely located PCs to work on small sections of very big data. And of course, there is no denying that money and human lives can be saved if we have accurate weather forecasting. I did mention to you about the collaborative aspect of our experiments. So these are huge experiments. And one big take-home message from this adventure is how to work in a collaboration, in a multicultural, international, global collaboration. And it's always taught me that 1 + 1 is equal to 11. And it's unbelievable that how to harness the power of a collaboration. This is something to learn, especially for people coming from my side of the world who may or may not have had that kind of an exposure, that kind of opportunities. But the way we collaborate is very different from any other large experiments that may exist on the planet. Apart from, I think, the gene program, I do not know of any other mega science project that has more than 5,000 or more than that scientists. So it's more about collaboration and a healthy competition. That's something that really one has to learn. And imagine, you can see that this collaboration has been extremely successful, and it has been successful because of many different rules that just come into play without speaking. They are just shared values that come into play, where we are not looking for singularities. We are always a team, and the team spirit and also the goal is one, and the goal of the whole group is beyond and above an individual person. So of course there are challenges, and there are challenges every single day, but this learning is very important. It has been very important for me personally. And of course, every time you have a problem, you can always go and knock a door or pick up the phone or send an email to find answers, of course. So personally for me, it's been a very enriching adventure, and I am now taking this further with students and my own group with whom I work. And it's really all about sharing whatever little I have learned. This is just a picture to show you, particularly for the younger people, that this is the next dream that could become a reality in the year 2040. So clearly it's not for me, it's for many of you. Here you see that this is LHC that I have described to you, 27 kilometers. And the FCC, the Future Circular Collider, will be a collider of 100 kilometers diameter. So challenges are there, and they are here for the taking. Now, many of you might think, oh, this is fantastic, I want to take part. And it is a very confusing and disorienting idea, I can imagine. Nevertheless, the best way to get started in this whole story is by becoming a student there, or just passing by, taking a look what's going on, whatever interests you. There are hardware projects and there are software projects. And this very big complex experiment that I described is divided into small units, smaller units that fit into each other, and there's always work to be done. And you see, there's so many students who are always coming, and I'm working together with them a lot. And you can see that these are my activities on the side as well, where I work with teachers who then train other students and so on. So this loop is working, and I'm very glad to receive students and also to receive ideas from you all. Now, of course, not everybody can come to CERN, not everybody can be brought here and so on. So we need to bring the exposure back home also. And the webinar is one way of doing it. So thank you for giving me the opportunity. So one last comment I would like to make is that particle physicists is a very sought after commodity. And I hope I have convinced you that it is a very multidisciplinary field. One can imagine that you're a computer scientist, or you are a hardware specialist, or you are a medical application specialist, or you can do an industrial application using safety systems, radioactive measurements. You can be a space scientist, and you can work in a bank doing risk management and financial management, because the kind of tools that you learn are applicable everywhere. Particle physics is a vehicle for you to make you realize your dreams in whichever field you wish to go. So passing through particle physics is definitely an adventure that you might want to at least take a look at. So I would invite you all to join the mission of CERN, where we push back the frontiers of knowledge. We develop technologies for accelerators, detectors, and information technologies. We train the scientists and engineers for tomorrow. And of course, we unite people from different countries and different cultures. So here I would like to stop and just remind you of my favorite poem from Robert Frost. The woods are lovely, dark and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. Thank you for your attention.
Thanks, Archana, for the wonderful, insightful talk about the particle physics and CERN activities, and encouraging people to get interested in this field. And there are some questions in the chat message I see. Could you please answer this?
Sure, yes. Please say your name and your question. Thank you.
I have to unmute. Okay, yeah. Yeah, please go ahead.
Yes, I just have a simple tactical question. When you want to schedule an experiment on the accelerator and collider, how long of a wait time do you have for that? What is the scheduling? 5 minutes, a day, a night, a year?
It depends on the experiment, you know, so there are phases. Initially, if you want to do R&D, so you might want to test a small detector. So you've got your own laboratory, or you've got master laboratories at CERN which specialize in certain technologies. So you might want to collaborate with them and work in those laboratories to do your tests that are short-term tests. So if you want to have a beam time, for example, to test your prototypes, then there are, in the accelerator complex, there are shootout beams which act as test beds. And you can request time in those test beams, which could be a week or 10 days or a month and so on. So those can be requested, and there is a program of test beams that is run, and the requests have to be done somewhat a year in advance, because you know all the resources have to be put in place. And eventually, if we are talking about very long experiments, then you need to first go through a committee that is called the Scientific Policy Committee, and you have to convince this committee that this is a very important and interesting and worth the time of running of the accelerator, where you can request beam time on the accelerator.
Hi, can you hear me?
Yes, go ahead.
Yeah, I'm Yonel Miu. So a lot of us here are because of a common interest in quantum computing, and I'm wondering how CERN is involved to help this field.
Yes, so I have to admit that as I did mention briefly in the beginning, that I was kind of overwhelmed that you are all experts in quantum computing. So, you know, I do not have too much knowledge about this. But from the little I gather is that CERN is very interested, and they have formed a forum of quantum computing with the experts from the IT department who are working actively on how to exploit quantum computers for high energy physics. And I know that this forum exists for the last 2 years. and that they are looking at ways and means into marrying the techniques that are being used presently and the techniques they want to prepare for the future. So if you want to have more details, I can put you in touch with the real experts. You know, if I say anything more, I will be revealing my ignorance.
Okay, so
And if
my
I
question
may
actually was
just answer, last year actually CERN is one of the few places that performed a quantum computing hackathon. So
Yes.
they had a weekend and people from all over the world were
That's-
flying to Geneva to work together on ideas.
That's correct. Yes, that was last year. Yes, that's true.
so. My question was okay. I understand that they want to use the quantum computing to evolve their computing, definitely. But my question was, since CERN has all the tools, they have the hammer, right, to answer the questions that are being trying to be answered by the industry, I would say, because you guys have all the tools in there, right?
Yes, I can.
Can I formulate your question more like what are the tools that are currently used in CERN that could be useful for quantum computing?
Okay, I
Is
can
that a
give.
good?
Yeah, I think I have understood the question, if I've understood correctly, that there is a certain area at CERN which is called Open Lab. And this
Okay.
Open Lab works very closely with industry. And they formulate problems like the ones you mentioned, and then they work together on finding the solution. So indeed, there are two people heading this quantum computing at CERN forum, and this is with the Open Lab, with the industries, and eventually looking for solutions for the future. So there are action going on, and perhaps in the future you might want to invite one of these experts to one of these webinars.
That would be great if you can give us some names.
Okay, I will.
Thank you.
Yeah, let's move to the other question by Swapnil. And Swapnil, please go ahead. Swapnil, are you there?
Hello, ma'am.
Yes.
Hello, ma'am. It's Swapnil speaking. I wanted to know how CERN can help to tackle coronavirus or such diseases in future. Means how can particle or any expertise from the CERN can help to mitigate these kind of diseases, because Europe has the epicenter of this kind of disease. Firstly.
Yes, Swapnil. So I fully agree that the biggest challenge and the crisis in the world right now is the coronavirus. CERN has an active task force for COVID-19, very active task force that is looking at various ways on how CERN can help the world to tackle the problem. I will not mention about the simple solutions like, you know, mask fabrication or ventilator. In fact, there is a new design made for ventilators and it is under production at the moment as we speak, which has been designed by our engineers. And but I would speak more in terms of how technology can be used. Communication technologies can be used. Data analysis and data modeling is already being used, and there is some program called Folding at Home. You may have heard about it. Is also CERN is using very heavily. CERN clusters are being opened for doing simulations. So yes, there is a lot of work that's going on in that direction. So directly, you know, we are not a biology lab or we are not a virology lab, but whatever can be done is being done with this COVID.
Yes, ma'am. I got to know that. Thank you. Thank you. Thank you.
Any other questions?
Seems chat, Sweta, Virajji. Sweta, please go ahead.
Oh, hi, thanks for the lecture. It was really interesting to hear about the work that's being done. It was really informative. I think, so for the, in the way that you're collecting the data, I was just wondering what the process of analyzing that data was for the the Higgs-like particle, and then how is that, what's going to be maybe different in the future with the FCC? in the questions that you're asking that would be different in future experiments?
So data analysis as such, the experimental collaboration is divided into various groups, as you could imagine. So there is a data analysis group, because I belong to the instrumentation group. You know, I'm engineering on the detectors, building detectors and so on. But then there is a dedicated expert group that is looking at techniques on how the data analysis can be aligned. They look at the various channels in which the physics processes might show up in the experiment, and all that has been studied very, very carefully. Over the last 25 years, you know, we've been building the experiment, but they have been simulating physics processes using very smart tools. You may have heard of Pythia and so on, where they simulate the whole detector and they simulate the physics processes. So they know exactly up to the 10th place of decimal probably on the kind of processes that should show up in the experiment. And given the energy at which we have been running now. And when we improve the energy, then all these simulations have to be redone, right? And then again, we have to look at all the different physics processes, you know, like decay into different particles, the branching ratios will be different, and so on. So there are dedicated people, PhD students, postdocs, faculties, professors, they form groups and they are meeting, you know, every week to make progress and then to charter the way for the future.
Okay. Yeah, thank you. That really helps. Also, I just had another question as how other students can be involved in knowing what the research has been so far. Is it like open sourced, or is it kind of you have to be inside the lab to know?
Everything we do at CERN is open source.
Oh, okay.
So there is just no secret here. You just need to go, you just type your question and you might just about find the answer, you know. Okay. So, all data is open source. So if somebody really wants to discover a Higgs for themselves, they can sit at home, they can log in there and they can look for data and then go and do their searches. There are master classes, everything is available.
Okay, so it's available on the CERN like platforms for.
Yes. In fact, if you are send me an email and then I'll put you in touch with somebody who can give you detailed information. Okay. I've given you generic information because I do know that everything is open access. Data is open access as well. We have released 2 years worth of data recently. So any student anywhere in the world can actually do any kind of research, or if they have ideas on new algorithms to test, you know, this would be fantastic.
Okay, thank you. Thanks.
Yeah.
Ma'am, I want to know, I'm Swapnil, if bachelor's student from engineering background can join CERN, or is it possible for them, or they should have possess master's degree?
So usually CERN has a summer program, which is a very sought after program. Unfortunately, this year for COVID-19 reasons, it has been cancelled.
Yes, I got to know that this year it has been cancelled. Yes.
Right. So, and the eligibility criteria is the 3rd year of the bachelor's, you know. So you should not have completed your bachelor's, but you should be entering, you should have had 3 years of university, whatever course you are doing. So that's the first entry point as a summer student. But apart from that, you know, there are many ways in entering the field. If you are placed in India, if I understand. So
yes, ma'am. I'm from India. I'm regularly following you. First, I saw you on NDTV, how you are encouraging students to go in science field. From that, I have started that journey till date.
Thank you, Swapnil. So what you can do is, you know, in India, there are many labs where collaborations exist with CERN, right? So
Yes,
if you look at Tata Institute, if you look at BRC, if you look at Delhi University, or if you look at IIT Madras, IIT Bombay, so there are many places where there is already an established program with CERN, you know. So
Okay.
you can do some projects over there that will give you more information, and you'll get to know the people. You can get to know what kind of experiments are going on, what are the opportunities, and believe me, if you want to, you will find it. You'll find the opportunity.
Yes, ma'am. I have already applied for Tata Institute of Fundamental Research in Hyderabad
Wonderful.
for that purpose.
Very good.
Ma'am, and I want to know, you have brother working in Tata Trust or someone
Yes,
from your family?
yeah, we'll ask those questions, personal things. Please
Yeah, okay.
keep this for forum only. So we'll go to the next question. Ridipala has asked about cooling of cosmic, so right time for lunchtime. So he was asking about elaborate on the cause of cooling of cosmic soup. There's a
Cooling
question.
of cosmic soup. Okay, so this is a kind of difficult question and difficult to answer as well, but I will try. So as far as I have understood, the universe has an inflationary stage. Okay, let me take a look here. And the universe is expanding. And we do not know if this is expanding or infinitely, or is it expanding and then it might be contracting and so on. So we do not know exactly whether this expansion is taking place or not forever. But in the first moments of the universe expanded because of the way the Big Bang has been defined, the singularity has been defined, and the particles have been observed and the properties of these particles that have been observed. So the cooling has happened because of those reasons. But to go into greater detail, one has to really study about inflation and about the expansion of the universe. I would encourage you to take a look, maybe just Google up some articles about this subject.
Thank you.
Anybody else? I see a lot
Hello.
of.
Hello, ma'am. Am I audible?
Yes, please go ahead.
Yeah, ma'am, it's Nibir. I wanted to ask one thing, like, do you expect to see some new physics, like some physics beyond the standard model after the high luminosity LHC upgrade?
Yes, certainly. I think there is a lot of room to see new things, and which is why we are upgrading the machine, upgrading the experiments, increasing the sensitivity of what we will be able to observe from the experiment. And there are hints that we might be able to see some new physics beyond standard model, and even figure out. I mean, if we are lucky, sometimes things just happen. So yes, we are definitely hopeful.
Yes, ma'am.
And I want to say this is well aligned with Dave's question. How may the Large Hadron Collider help people understand dark matter?
Yes, so candidates of dark matter, however difficult, but if we are lucky, we might find it. But the only thing is that the way a dice, when you roll a dice, the chances of getting a 1 are 1/6, right? But if you roll a dice, and if you have a dice which has 100,000 sides, then the probability of finding that will be 1/100,000. So we just need to increase our data. We need to increase the sensitivity of our apparatus and all the systematics, improve the analysis techniques, and we came a long way in finding the Higgs boson. Remember that in Fermilab they did not find it simply because they did not have the sensitivity. They ran for 10 years and they did not find the Higgs boson simply
Hello,
because.
ma'am. Can we have such kind of sessions also for another time, and means for different topics of CERN also?
We can have
this kind of session also helps us to understand more.
Certainly, they will help everyone. So we could have a question and answer session only, perhaps, in the future.
Can I ask a question?
Yes, please.
Can I ask a question?
Yes, please go ahead. Okay. Yes,
Hello?
you're on.
Please
Hello.
ask a question. Yes, hello.
Oh, if you're listening to me, to what extent does it make sense to ask if there's a mass up to which work at CERN has pretty much reduced or eliminated the possibility of finding new particles? And if so, sort of where's that limit today?
That limit. Okay, I think I'm not up to date with all the analysis that's going on, but I could safely say that at least up to the Higgs masses, we have eliminated or at least made boundaries up to where we could find new physics. But of course, searches are still going on, analysis is still going on. So I'm afraid I will not be able to give you a very precise answer. I might find it, and maybe in one of the next sessions I could tell you, but I wouldn't want to give you any wrong answer.
Thank you.
And this work is still going on at some places, or it is shut down due to COVID-19, or the people are still working there.
So people are only the people who are absolutely necessary to keep the lab in a safe state, you know, because we have very big machines, as you can imagine, and we had to shut them down in a hurry pretty much. So we are trying to ensure that the lab and all the material in the lab, all the machines in the lab, they are in a safe state, which means, you know, that if cooling is needed, then the cooling towers are working. If power
Yes,
is
yes, yes.
needed for the magnet, then that's working. So like the essentials. Out of
Essential
all,
thing.
out of all the thousands of people, only a few hundred are actually allowed with very strict protocols on how they can enter. Right?
Yes, I also read that CERN is trying to make, scientists and engineers trying to make ventilators for the people. That is
Yes,
also good.
absolutely. Yes, one design is already out, and
Yes,
that
yes,
is,
I saw that. Yes, I saw that.
yeah, one of our colleagues from LHCB has made that.
Yes, yes.
My question is about fusion technology. I'm interested in the cold fusion, hot fusion. So how CERN is involved in any of the power generation areas like fusion area?
Actually, there was some collaboration that was working in the direction of fusion. However, I do not think that recently there has been any advance. Over the last 10 years, I would say the focus has completely been on the LHC experiments. So on fusion, there was some talks and some work done, but really nothing that I can report to you.
I would assume that because of the big project that was initiated in France on
Yes.
fusion, this
Yes.
probably shifted the focus.
You're right. Yeah, that ITER project is going on, and a big community is working over there. So it's a duplication, you know, in some sense.
Excuse me,
Yes,
am I audible?
Aditya.
Yes, ma'am. I had a question on FCC. So, is it I saw the radius of FCC was much greater than LHC. Is it like bigger the better?
It's yeah, in the sense that imagine that you have a stone that is tied to a rope and you are turning it around, right? So if the string is much larger, you will be able to acquire more energy, isn't it? Although there will be losses as well. So there is still a lot of discussion going on, and I think next year or this year probably the decision will be taken on what kind of particle will be used for that collider. But certainly if you have a larger radius, larger circumference, you will be able to have larger energy. Your gain in energy is much more as compared to a linear collider.
But if the string is long, the kinetic energy of the particle decreases.
Yeah, so but then on the other hand, your acceleration that you will get because of the magnets will increase like, at a lower magnetic field and to the square of the length of the radius, in fact.
A simple example is if you think when you are biking and the faster you are moving, then the bigger turn you make, because if you try to make too sharp of a turn, you fall down. This is just inertia. The more energy you have, the harder it's to bend this straight line that the particle would like to go. And it will take you more energy to do that.
Thank
So take a look at, I will maybe find something and I will send you if you get in touch with me. I have another slide on that.
Ma'am, one more question.
Yeah.
Ma'am, when we talk about fields like Higgs field, ma'am, is it analogous to like gravitational field or electrostatic field, elementary fields? Like?
Yeah, a field is a field, in fact. So, so gravitational field, magnetic field, electromagnetic field, strong fields. Whenever there is a, how can I say, you have a gauge particle, which is actually a boson, it is actually a carrier of the field. It's a force carrier. So it is very much a field which is similar to the other fields. However, the way it operates is a bit complex.
Oh.
Excuse me, ma'am, am I audible?
Yes.
Ma'am, I wanted to know what are the near future goals of LHC? Like, can we expect anything exciting or like that for next
Absolutely.
5-6 years?
So we are spending so much money that has to be very exciting, you know.
Yes, ma'am.
So we are, at the moment, the LHC is in shutdown mode. And due to COVID, there will be another delay of 1 more year, probably 1 or even 1.5 year, where we are upgrading the cavities of the accelerator. We are going to have the experiments upgraded as well, and the energy at which we will restart the machine will be, for initially it will be 6.5, sorry, it will be 70, it will be 6.5 on each proton beam, which means the 13 TeV, and finally it will go to 14 TeV, but the luminosity will increase, which means that we will have many more collisions per per crossing. We will have many more collisions. So the cross section of part of the processes that are very rare will give us data set will be ready to give us more physics. The harvest will be more rich, and then of course the analysis will be rich as well, right?
In this respect, I think there is another question, Radif Palai asking about accelerator or LHC's major so huge. Then how are the maintenance sessions of particular part carried out, as it doesn't disturb the environment inside the setup?
Yeah, so this is a very good question, and of course it is thanks to the excellent design by the accelerator engineers, by the experimental engineers as well, that they have made it modular in such a way that maintenance can happen very regularly. The timetable of the accelerator is such that it shuts down every year at the end of the year for 3 to 4 months. And all the maintenance and upgrade, the regular maintenance and upgrade takes place at the end of every year. Then it starts being operational somewhere around February, March, and it runs until September. So that, you know, that's the running period, and then you have the maintenance period. So every year this is done very, very regularly. In addition, I think every week there is also a day, which is a maintenance day every week. So, you know, if there are interventions that are needed, absolutely, those are done very regularly. Thank you.
Hi, ma'am. Hello, ma'am. This is Vinayak from Bangalore. So I have one small question. So in CERN, any experiments are done related to neutrinos there? neutrino
Yes,
particles?
neutrinos, there are several, let's say, communities at CERN which are the world experts on neutrinos. There was an experiment called Opera, you may have heard, that sent a beam from CERN to Gran Sasso in Italy, 700 kilometers away. And their oscillations in the tau neutrino were found. So that was a very incredible experiment as well. There are teams that are preparing for the Dune experiment at CERN. So a proto-Dune module has been created, and then that has been shipped to Dune in the United States. So yes, there are lots of activities going on in the neutrino as well.
Yeah, thanks, ma'am. And one more small thing. So if someone wants to start learning about the particle physics, so where one should start?
So I think there are, of course, many books that one can read, but the best tools today are, of course, very interesting lecture series that you can find on the web. If you go to the website of CERN itself, there are public pages. You start from there and then you start digging into references from there.
Yeah, thank you. Thanks a lot.
Yeah.
Ma'am, one more question, that how computer science background students or engineers can participate in or do research in particle physics?
So as you have heard that there is a lot of work that goes into making tools for doing particle physics, right? So the tools are not like accelerators, the detectors, and then IT. IT is a very big section where we need algorithms, we need techniques, we need databases, we need data analysts who are very, how can I say, dedicated on creating networks, neural networks, machine learning, artificial intelligence, and so on. So there's a whole, plethora of things to be done by a computer scientist or computer engineer. And there's lots of room to do work in particle physics. So particle physics, imagine you are creating a space shuttle. So then you need all sorts of tools to have that ready, right?
Yes, ma'am, yes.
Any other question? Otherwise, we can try to wrap up.
Ma'am, and when will be the next session coming soon?
You have to ask the organizers this question. Organizers can answer, I suppose.
Okay, ma'am. Okay, thank
you. Am I audible?
Yes.
What are the causes or like scope of error, as the setup is so huge? So how is the efficiency made, like every time you carry out a reading or you take a reading?
This is a very important question, and of course this is also part of the awe of this adventure. Some pieces are built in Russia, some pieces are built in China, some are built in US, and then they all come together. Then they are brought together at CERN, they go underground, and then they are aligned to within a millimeter, right? After that, there is a calibration that is done for the whole experiment to understand to within 100 microns and sometimes to within 10 microns where you are actually measuring the tracks that are coming out. So this itself, the alignment, is a very big area of work for the experimentalists to make sure that every time you measure anything, you are measuring it correctly. And every time you take data, there are alignment files by which corrections needed to be applied on every set of data. So yes, it's very, very important, and you need to be very aware of the fact that errors do not creep in. There are systematic errors, there are statistical errors, and every instrument that is there, as I said, the cylindrical onion, and I didn't get to describe it, but you can imagine very clearly that there will be errors when you move from one system inside the CMS detector to another one outside. How do they communicate with each other? And physically how far apart they are. But the track sees we know from physics analysis and from the simulations how the track will behave in a material, you know. And so that also gives us handle to correct where the track should be and where the track is. All right.
And one more question, like you said that you mentioned that LHC is a discovery machine that will work till 2035. Like, why so? Is it
Well,
lifetime?
no, it's a planning that can be done. And how much planning can you do in the future? So at least up until 2035, there is a plan. And
Oh, I
maybe,
thought there's some scientific reason. Okay.
no, well, at least from what we see at the moment, from competing resources, from competing experiments, from the physics that one can do until that moment. Because you see, in the world, at the moment, there is only one LHC. Suppose tomorrow there is another machine like this that is built in another country. So usually up to today, up to now, the world has been working together. If there is a machine in the United States, the next machine, which means the next generation of the machine, will be built somewhere else. So that, you know, there is a handshake between the physics that you are working on. The top quark was found at Fermilab, and the Higgs boson was found at CERN, just because of the parameters, how they have been designed in such a way that, you know, CERN will not build a machine that is equal to the machine at Fermilab, right? So this was a next stage. And the future machine will be built larger than the LHC, or maybe radically different and maybe much smaller with some brand new technology, but different energies, but nevertheless always handshaking with the physics that has to come in the future. So up to now, up to the foreseeable future for the LHC, and given the nature of these very large projects, you have to plan much in advance. If the FCC has to start in 2040, or at least the construction and so on, then approvals need to happen now onwards. You know, it's just 20 years ago, 20 years in the future. LHC was approved in 1984, I think. The tunnel was approved, and the LEP machine ran until 2000, until the year 2000, and then the upgrade of the LEP was the LHC machine. So you see, it's like a chain that links and keeps the physics, keeps the science moving ahead.
Ma'am, my question is that, as we have seen with the countries like United States, that when government changes or the political leader change, they have to make changes in their projects, and they face problems for assigning a project for a so they face problems in deciding a long-term project. So do you also face such kind of problems in
Every day we face this problem, because right now, if you imagine that we have our projects that are aligned to be delivered, but countries have stopped. We never expected this at the moment, right? And we do not know when the priority will be back on physics. First, we have to solve the other problems of the world. So yes, there are these kind of issues that come up all the time. And of course, governments change, and sometimes the party that comes in power does not have the same view on how to spend the money. And it's a constant fight by our spokespeople, the director generals of our institutions, who are constantly fighting to justify what we do has an impact on society. And what we actually do, it has been measured that every dollar spent in high energy physics brings back $4 to the society. So it's a lot of hard work that people have to do in terms of establishing, first of all, their own experiment, the credibility of the work that they are doing, the priority of the work that they are doing, and the impact of that work in the society.
Ma'am, one more question I would like to ask, like how seismic vibrations like earthquakes disturb the setup?
You're absolutely right. This is a very important point, and indeed, earthquakes will disturb, certainly. And it's not only earthquakes, even the movement of, the moon, the movement of trains around the region, they induce fields that are actually affecting measurements. And fortunately, this can be measured. This can be also simulated. And I think I have read a report in one of the bulletins long ago on the correction that has been done to the beams because of the movement of the train, the TGV trains that move from Geneva to Paris. So yes, it is a very important point. We have to track every movement. That's what happens. And nowadays, science has advanced so much that we are able to predict what should happen and what has happened. And those two should fall on the top of each other on a graph.
Is there a specific reason behind selecting like Geneva only for this huge setup?
So there are several reasons. The first reason is that Geneva happens to be a place where there is the United Nations, and you know that before, after the Second World War, scientists were running from Europe because of the situation after the Second World War. They were running to the United States. So governments and people in Europe, they came together, scientists came together, and they created a center called CERN in Geneva, just for the fact that the United Nations headquarters was over here. And once it was established, it was also found that the terrain where CERN is has a massive plate, you know, there are molasses underground, and then there is a very big granite block. So this granite block underground creates a very stable place where you could build an accelerator. And in the end, that's where we have the accelerator.
There's a question about black holes. Somebody asked, I think, Pramod Bhatt, are you there? Hello?
Yes.
Yeah, please go ahead with your question.
Hello, ma'am.
Yes, hello, Pramod.
I wanted to ask why do we cannot capture the existence of micro black holes?
I didn't get the question. I just heard.
Why do we cannot capture the existence of micro black holes?
Why we cannot? Okay. As far as I know, I'm not an expert in the subject, but the black holes are destroyed when they are created, probably, right? And in the LHC, we cannot measure because the energy that is needed to create it could be very, very tiny, so tiny that the creation and the instant disappearance is blocking us from any way of actually looking at a black hole.
And conceptually, that there's a issue with the fact that usually a black hole is presumed to have a singularity.
Yeah.
When in quantum mechanics, we usually recognize that singularities disappear, they are kind of smeared out.
Right.
And that's why people are considering quantum gravity, that would be a resolution of the singularity in a black hole.
Right.
So it could be that the quantum mechanical effects are preventing the formation of micro black holes.
Ma'am, I also wanted to ask the question.
Yes.
Does the location of the LHC can affect the experimental results?
Location, you mean geolocation? It should not, because in the end, physics is physics. So wherever you make your machine, you will have to do all the work that is needed for making your analysis and your simulations. But physics is physics. You know, the rules will not change if you go from place to place, right? Okay.
Thank you, ma'am.
I think we are exceeding the time, and we have to conclude this session. We can have another session for question answer for after 2 weeks or something. We'll communicate this after confirming from the speaker Archana, and we'll announce that later. And right now, we have to conclude this session because it is going beyond 1.5 hours. I think it is. It'll be we are giving more questions. It takes more time, so we'll conclude here. And thanks for attending the event, even on the weekend. And I thanks to the speaker Archana also to explain about the CERN. And we are excited to hear more, I hope, in future.
Yes, yes. Thank you for info. It was very informative and such nice to listen to something like this.
Thank you very much. And next time I will try to see if I can answer more questions. Thank you very much for inviting me. Thank you, Balaji. Thank you very much.
Archana, and,
thank you, ma'am. We are all proud of you.
Yes, ma'am. We are proud of you.
Thank you, everyone, for your participation, and thank you for the wonderful talk. It was a pleasure to meet you.
Thank you. Pleasure is all mine, and I mean I'm privileged to be interacting because that's what gives me very, a lot of pleasure. Thank you. Bye bye, everybody, and take care. Bye.
Take care, everyone. Take care.
Bye.
Bye.
Bye. Bye.